So look at another theorem. This theorem says that for any non-zero constant k and an invertible matrix A, we have this property that if I multiply k with A and take inverse, or if I divide k by 1 and then take the inverse of A, we will get the same result. There is no change. So we have to prove this theorem. So look at the proof. So before going to the proof, since our aim is to show that this is the inverse of k times A, right? So in order to prove that this is the inverse of this, we have to multiply both. If their multiplication gives us identity, that means we have proved the theorem. So what will I do? I will multiply this, the matrix inside, and this matrix. So let's do their multiplication and check whether we are getting identity or not. Since this is the constant, this is also a constant, so I can multiply both constant here, and this is the matrix and this is also a matrix, so I can multiply both here. Since this is k and this is 1 over k, they will be cancelled out and I will get only this multiplication. You can check here. Since A and A inverse are inverses of each other, so they will multiply to give us identity. So this is the proof. I told you if I multiply this thing and this thing, and if they give us identity, that means this is the inverse of the matrix inside, and we have multiplied them and we got identity. That means we have proved the theorem. Now let's move towards an example. In this example, we are given a matrix A and its inverse also. Our aim is to verify this theorem. This is the theorem which we have to verify. So we will verify this theorem for k is equal to 5. Okay, let's do the verification. In order to verify, we have to prove that 5 times A whole inverse must be equal to 1 by 5 times A inverse, because this is the statement of the theorem. You can see it again. So what we have to do, solve left hand side and then right hand side, and we will expect that both sides will give us the same result. So let's do the left hand side first. In the left hand side, I will compute this thing, 5 times A whole inverse. Now if I put the values 5 as it is, then A, the value of A, then the inverse, you can check. So now first I will multiply 5 inside, and then after multiplication I have to find the inverse. So in order to find the inverse of this matrix, I have to do consider an augmented matrix, and in that augmented matrix, here I will put the same matrix and here I will put identity matrix. So my aim is to convert this 10 into 1 and then this 15 into 1. How can I do that? If I multiply R1 by 10 and R2 by 15, then I can get the result. So I have done division by 10 of R1 and R2 divided by 15. So after the division, here I got the identity matrix. and this is the inverse of that matrix. So hence I can say that the inverse of the matrix inside is this matrix which we have got. Okay, so our left hand side has been computed completely. So the answer of the left hand side is this which we have got. Now let's compute the right hand side. In the right hand side we have 1 by 5 times A inverse. Now since we have already given that A inverse is equal to this matrix, you can check. So now we have to just put the value of the A inverse. Now what will I do? I will do multiplication of 1 by 5 inside the matrix. If I multiply 1 by 5 inside the matrix with each term, since if I multiply with 0, I will get no change, and I have multiplied 1 by 5 with 1 by 2 and 1 by 3. After multiplication and simplification, I will get this result. Now let's check whether this result is the same as the left hand side or not. You can check. This is the left hand side, which is 1 by 10, 0, 0, 1 by 15. And the right hand side is the same. Since left hand side and right hand side are same, hence our theorem is verified. Now let's do another theorem. In this theorem, we will again have an invertible matrix. And for the invertible matrix, we have to prove that whether I take the transpose first and then take the inverse, or I take the inverse first and then take the transpose, I will get the same answer. Look at the proof. In order to prove this theorem, we have to verify that if I multiply the matrix inside with this matrix, I will get the same result. I will get the identity matrix, because this matrix is the inverse of the matrix inside, because it is A transpose inverse is equal to this. This means that this matrix is the inverse of A transpose. So if I multiply A transpose with this matrix in this way, you can see I should get identity. Okay, now look, if you see that we have two matrices, this is one matrix and this is another matrix. Let me change the color here. This is another matrix and this is another matrix. Sorry, this is another matrix. So you have this scenario: A transpose B transpose is the same as B times A transpose, or yeah, this is the theorem which we have already proved earlier. So if you think that this is A, if you think that this is B, so what does this theorem says? I will write B first and then A and write the whole transpose. So this is our B, so I will write A inverse first and then I will write this A and then I will write the whole transpose just by looking this formula. Now I think this is clear. Now if I multiply A inverse with A, I will get identity, because A and A inverse are the inverses of each other. So what is the transpose of the identity matrix? Since the identity matrix is nothing but this thing, 1 1 1 along the main diagonal and everything 0 up and down. So if I take the inverse of this identity matrix, what will happen? This 0 will come down and this 0 will go up. So what will be the change? There will be no change. I will again get the identity matrix. So if I take the transpose of the identity matrix, I will get the same matrix. There will be no change. So since I have multiplied this matrix with this matrix, after multiplication I got the identity matrix. This means that this matrix is the inverse of the matrix inside. Hence, this theorem is verified. Now we will solve an example which is again based on this theorem. In this example, we are given the matrix A and the matrix and the inverse of A. We have to verify this theorem, the theorem which we have just discussed now. So let's do the verification. So in this example, we have to verify that A transpose whole inverse is equal to A inverse whole transpose. Okay, here is the verification. So in order to verify, we have to consider the left hand side first. If I consider the left hand side, and if I put the value of A, so I have just put it the value of A and written the transpose as it is and written the inverse as it is, no change. So if I do the transpose, so what is the transpose of this matrix inside? This is the row 1 1, so I have written 1 1 along the column, and this is the second row 0 1, I have written this along the column. So I have taken the transpose and written this inverse as it is. Okay, now our aim is to take the inverse of this matrix. In order to compute this inverse, we have to consider an augmented matrix, such that here I will write this matrix, and here I will write the identity matrix of the same order. Now my aim is to make this matrix identity. How can I make this identity? If this is 0, then this matrix will become identity. How can I make this 0? It can be 1 minus 1. What does that mean? R2 minus this one is coming from R1. So I have to perform this operation, R2 minus R1, R2 minus R1. So I will make no changes in R1. I will make changes only in R2. So 1 minus 1, 1 minus 0, 0 minus 1, 1 minus 0. So the only changes which I have made are in R2. So after the change, making these simplification, I will get here identity, and here I will get this matrix. So what is the inverse of this matrix? It is, so the inverse of this matrix is equal to 1 minus 1, 0, 1. Minus 1 here. So this is our left hand side. Now I have to compute the right hand side. Okay, let me write the left hand side is equal to 1 0 minus 1 1. Now I have to compute the right hand side. In order to compute the right hand side, I have to first take the inverse of a matrix, and then I have to take the transpose. Since the inverse of a matrix is already given, which is 1 minus 1, 0, 1. So the inverse is already given, 1 minus 1, 0, 1. So what I have to do, I have to take only the transpose. So if I take the transpose, this row will be changed into column 1 minus 1, and this row will change into the second column. So this, the right hand side is also computed. Now let's check whether the right hand side is the same as the left hand side or different. So you can check both are the same. Since left hand side is the same as the right hand side, hence the theorem is verified. And this is done.